Dobro. Oprostite, ovdje je ovo predavanje sad o tapanju ledenjaka, jel da?
Valentina?
Da.
Da, je.
Ok, hvala.
Može. Tu ovaj sivi kabel, šta je pokret konvice. Da, ne.
Ja, sam imam malo sora sad neki. Ali puš možeš je super, meni će se... Da, meni će tako... Da, to će biti po stepenicama. To je psihološki. Baš ima ono, sam to zove delay onset muscle soreness.
Delay onset
Muscle soreness.
D-O-M-S.
Nemaš neki onaj...
Nemaš neki onaj... Dums.
Mislim da je ono pravo, ali to mi baš ne želi reći, da je pravo ću staviti ne upravo.
Dakle, kad ćeš ti pa daj, to ćemo uzeti.
Meni je uvijek godine, ali imam problem. Kad sam bilo ne, tu si ovaj...
Vidjeli sam samo ovo sliku.
Ne.
Zašto? Skaj za nevidljivost.
Moram ti to ne znati objasniti, kada ti? Da. Vjerovatno je i to. Da je sve na listi, ne mi čudilo da je i to. Ali baš sam komentirati s Cimerom, ne znam koji imaš.
Aha, pa ne si ti javno.
Možda sam ja zapravo, možda sam to uzeo kao da bolje idu ispiti, ali možda je to za svi put, jer ono su svi bolje rešili ispiti.
Pa da.
Možda sam ja i dalje ono još uzeo.
Dobar si support, šta bi ti rekao?
Ja sam super
Ti
super.
strana nas deep alpha.
Ne želim ja vas dipa, sam sve dva. Čak mi je ok ako vas bafamo manje.
Znači da ti si rad deep alpha.
Evo ti
Pišeš medijan i...
a ne, ali samo svoj klip. Ne, da na cijeli svijet dijela je onda da. Ako hoćeš recimo četvrtu godinu, ne. Koliko sam ti dužan?
10.
Isto, kako je.
Dobar dan, tu je omladina stigla, bravo, da. Malo kolega da ste opisujete sebi na kud tako pozadijete svijest.
Postavimo pametnije.
To je krivo. Nisu pametni, jasno. Dakle, vas dvoje ćete biti na seminaru dinamički, jel? Da.
Imam 20, tako da okej,
Vidimo se već.
Jel možete mi probati još ono tamo malo jače za svijet? Ono zadnje ne... Jeste primijetili kako je ova južina prije 3-4 sata počela onako od jedan zviziti? Neobično. Znači se valjda noćas ispada da budete gotovo. Kako ste se pohvalili kolegama da ste položili dinamiku?
nije da se to hvali bila. Stvarno nije da se hvali. Ali ja još četvorku ću prvo bolje, pa možda se bude zahvaliti.
To smo i čuli, jesu.
Je.
Sve nama može da se predijao, da se u glavi domenički integrirao. I to kompleksno.
Ti se zezaš, ali...
i da si...
Ja sam numerički integriran. Na tamo, na klasičnoj. Da, sam rekao tamo i lijepo, mislim da vam je krivo ovaj integral. I onda je rekla isto da bi se čini da je krivo, zato što smo da je krivo. Ja sam dao na pamet rješenje. Davno je to bilo, onda sam još bio sposoban.
Drago mi je da ne radim diplomski iste teme.
Ja ne znam da je pa možda uzeti isto. Ja moram uzeti isto. Ja želim miješanje fluida.
A to je...
Ja mislim da je moguće.
Je to bio pretpostavka, da se kao ovako fluid jednostavno povezan, ali jednostavno povezan nije. Ili ako ima jednu ruku, onda ima jednu ruku.
Znaš,
Gustoća? Pa kažem kada imaš moj fluid, bilo kaplje vode se iskoči van. Možda to će biti na ovo malo.
Je li kamera prenapadna?
Nije. Gdje je najbolje zastajat?
Tu uz vrata, u pravilu. Tu vam je tipkovnica najbliža. Da.
Dobro.
Kadar koji se hvata se skroz tu do...
Ako nešto pokazuje?
Super.
Ok.
Mislim, možete doći baciti toliko, čisto da imate dojam.
Ok, ja nekako malo šećemo da neće biti.
U principu glas je bitan.
Dobro.
I ono, ako nešto pokazujete šta će se vidjeti, jer hvata se cijela kabel se hvata po još 10 cm i tu do štoka, tako da.
Već od snimanja, poštovanje, ja sam Valentina Radić. Na trećem programu Hrvatskog radija radim znanstvenu emisiju. Ja sam se s nekim tu sa odsjeka bila dopisivala, pa su mi rekli da će mi predavanje, da ćete govoriti na engleskom. A da će odgovori i pitanja govoriti na hrvatskom. Da bi shvatila. Mislim, ja vrlo često snimam predavanja i onda od njih radim emisije, ali za vaše predavanje na engleskom nemam šta predavati. Nemam mogućnosti ja to prevesti. Dakle, ono što bih ja radila da predavanje završio, imate da da mi snimam odgovore i pitanja, i onda bi s vama sjela 10 minuta. Zato da mi samo ovo što ćete naravno sekundi. Ne ostali stvari reći, ali kažem, ja bih se snimam odgovore i pitanja, ovaj dio koji ćete govoriti na hrvatskom, da ćemo onda to moći nekako inkorporirati. Kad počnete dio sa govoriti, ću se svoju oprebu staviti, ja se možda malo nema problema, čisto da znate, pa kad završi onda možemo svesti kad se isprazni i malo što se više. Pa super, hvala.
Šta? Da. Biće dobro da može zatvoriti, da mogu salu pretjavati.
Hoću samo pojasniti neke stvari što se tiče novog studenta, znači mi se počeli nekako kao
Valentina, kad si ovdje studirala, i niste ništa učili u katobatici, jel? Velika skala.
Znači, to je odradila, ti si napravila neku skriptu, ne znam je tamo.
Tamo ima napravila, malo smureno.
Da, ono baš tako se svoj, ne znam nekako se je bilo na način, znači
to je sad sve popularno. Radali su sutra na dinamičkoj.
Ništa, rada ipak krenula, doduše ne možda jednom uvodnom vješću, oni koji su na listi tehnološkog društva u principu znaju što se dogodilo. Ovog vikenda s nedelje na ponedjeljak je preminuo jedan naš kolega koji je dugo godina bio zaposlenik na Geophysical odsjeku, dr. Josip Jonas, tako možda započeli samo sam gotovo šutno. Drugi dio znači, je orijentiran više na ledenjake, na analizu katabatičkog strujanja. Evo, naš kolega, naš profesor Branko Krsobina ima gošću. Isto tako, naša bivša studentica geofizičkog odsjeka, sad prepuštam riječ Branko da malo objasni točno o čemu se radi.
Meni je baš čast i zadovoljstvo da mogu ovdje pozdraviti Valentinu Radić. Ona je ovdje diplomirala kod profesorice Nadežde Šimik, to je bila ova Hilbertova transformacija, podaci grički, i onda je otišla u Švedsku na takozvani licencijat. Mi to nemamo ovdje u našem obrazovanje, to je nešto između magisterija i doktorata. Na Štokholmskom fakultetu je to radila i završila uspješno 2007. A onda je otišla na doktorat u Fairbanks, Aljaska, gdje je odmah doktorirala 2008. U tom periodu se bavila, čime se i sad manje više bavi, a to je ono što uopće nije ovdje učila. Ovdje nije bilo katabatike, ali bila obrada podataka, bili su modeli. Tako da, kad čujemo kritike o našem obrazovanju, ovdje što ja puno čujem nerijetko, to je prilično iskrivljeno i obično je gledano iz pogrešnog kuta. Ako neko hoće s njim o tome dalje, to možemo kasnije. I onda moram reći, briljantna karijera nakon ovog doktorata u Fairbanksu, onda ide postdoc na UBC, University of British Columbia, to je u Kanadi, Vancouver, docentura i sad izvanredna profesura. Uskoro ćete čuti da ovdje ima jako puno meteorologije, a nije meteorologija. I da će ovdje biti dosta o katabatici, odnosno posebno vrsti katabatike, a to su ledenjački rijetkovi. Zašto je to važno? Zbog klimatskih promjena, jer možda ih uskoro nećemo moći ni proučavati. To je tako rapidno da možda to neće biti, ali bolje da neko o tome govori ko zna glaciologiju, ja nisam glaciolog. Valentina?
Ja se zahvaljujem što ste svi došli i ja ću se prebaciti na engleski, jer mi je stručni hrvatski totalno zakržljao. Mogla bi se još potruditi, ali eto, lakše mi je to sve izvesti na engleskom jeziku. So today I will talk about my long-term research program that is focused on how mountain glaciers around the world respond to climate change. In particular, my PhD research and still my ongoing research is on modeling glacier contribution to stream flow and to sea level rise. On this long journey, I had the privilege to collaborate with many amazing mentors, colleagues and grad students, some of which I listed here. So if I'm going to talk to you about glaciers and how they respond to climate change. First question is, why should we care? Why care about the glacier and the future of glaciers? So the glaciers and their future matters on many scales. So on the global scale, glacier mass loss is a significant contributor to sea level rise. So when I speak about mountain glaciers, I'm speaking about all the land ice, all the glaciers that are outside the large ice sheets of Antarctica and Greenland. So here on this plot, these blue dots would be where the mountain glaciers are around the world. There are approximately 200,000 glaciers worldwide. Glaciers currently contribute, their melt contributes about 30% to the observed sea level rise. So this is from the IPCC 2013. The measured sea level rise, which is currently the rate is about 3 millimeters per year, which doesn't seem a lot, but if you think about over the last 3 decades, that contributed 10 centimeters already. So basically 10 centimeters was the global sea level rise in the last 3 decades. So 30% of that sea level rise is due to contribution of mountain glaciers. The other 30% is from the ice sheets, from the melt of the ice sheets, from the mass loss from the ice sheets, and the remaining is from the thermal expansion. As you warm up the ocean expands. On the regional and local scale, glaciers or glacier melt water is significant contributor to seasonal stream flow. So they are significant freshwater resources. Especially they can modify stream flow properties, so river stream flow properties, physical properties such as runoff quantity and timing, and also biochemical and biological properties. So with this brief relevance on glacier importance, this brings me to my research questions that I will address today. First one is, how much mass will glaciers lose by the end of the century? The second one, what are the key uncertainties in the projections of glacier contribution to sea level and to stream flow? And then how to narrow the uncertainty in these projections. So starting with the first one. Before I go into the depth of answering this first question, I want to introduce some basic concepts that we use in glaciology so that it's easier to follow my talk. So the most common term that we use when we talk about glacier response to climate change is the glacier mass balance. So that's effectively change of glacier mass over a given time period. If this time period is 1 year, then we speak about annual mass balance, which is the difference between annual accumulation, mass gain, and annual ablation, mass loss. So the processes that contribute to, the dominant process that contribute to accumulation is snowfall. So glacier feeds on snowfall. But there is also wind-drifted snow, avalanches, and resublimation as processes of accumulation. The ablation, the dominant process is surface melting, but also there is melting at the bottom of a glacier. There is also wind erosion and sublimation. And also if glacier terminates in a lake or in the ocean, we speak about iceberg calving, so also loss of mass through calving. So the general concept here is that over 1 year, we have more mass gain than mass loss in the upper part of the glacier. And we have more mass loss than mass gain over lower parts of the glacier. And then therefore we have this, the mass balance gradient as a mass surplus higher up and mass deficit further down. And this imbalance, because of gravity, is then distributed through the ice flow. So there is an ice flow, basically the glacier is deforming, it's flowing and sliding, and also the formation of ice, due to this imbalance in the mass along the slope. And so the ice is flowing due to gravity. When we speak about, so now if we talk about glacier response to climate change, so if this glacier-wide mass balance, so the mass balance over the whole glacier area, if over a longer period of time this mass balance is approximately 0, then we say that the glacier is in equilibrium with the climate. If this glacier-wide mass balance is negative, we are talking about glacier retreating. And if it's positive, you're talking about the advancing glacier. So now, since I will be talking about projections and modeling, I want to introduce this modeling framework, which I've simplified here in this modeling flowchart. So what kind of components are necessary to model when we want to, let's say, assess the glacier volume change and then contribution to sea level rise? So we are starting with a signal that is the global signal. So global climate change, starting from the signal in the global climate, that then needs to be translated in the local climate, which is then a driver of the surface mass balance, which coupled together with the geometry changes of the glacier, that also is dictated by the ice flow, will result, so this coupling will result in the total estimate of volume change or mass change. And when we speak about the sea level rise, this is kind of fancy, but what we want to say is we talk about sea level equivalent. So that's effectively the volume change, the calculated mass change divided by the area of the ocean. So how much that volume change, if it's all dumped in the ocean, how much will that contribute to sea level rise? So we talk about sea level equivalent, assuming that everything that melts ends up in the ocean. So this, coming back to here, so a part of this surface mass balance modeling, so this will be the models of glacier ablation and accumulation. In terms of ablation, the dominant process is glacier melt. There is a large range of models for glacier melting, for calculating glacier melt. Here just briefly showing the full, but there is a large range of models in terms of their complexity. So they are the simplest models, they are empirical models, or also called temperature index models, and then more advanced models that are physics-based models that incorporate surface energy balance, for example. What's important on this chart is that the model complexity requires, as the more complexity in the model, there is more requirement for input data in the model. So effectively, the choice of the model will be dictated by what data is available. Similarly to these melt models, the models for simulation of geometry changes of the glacier, so how a glacier is thinning, how a glacier is shrinking, and then ice flow as well. is again like full range of models in that area. So we have a simple relationships between glacier volume and area, that would be the low complexity models, and then solving Stokes equations effectively, that we are going into multi-dimensional or like one-dimensional ice flow models or higher degree ice flow models. Again, the same as before, model complexity requires, as the model complexity increases, requires more input data. So, since I'm speaking about this importance of ice flow and the geometry changes incorporated in the surface mass balance, I want to give you just this concept with this cartoon, what is the effect of glacier geometry changes on glacier-wide mass balance and runoff. So effectively how much meltwater is produced from the glacier. So if we take the simplified cartoon, this is the profile, side profile of the glacier, and this color scheme here represents the temperature lapse rate in the atmosphere. So we will focus, and here I'm just showing the what I'm going to talk about next. So if we introduce a given climate signal, let's say climate warming, what this signal will cause glacier to do is the glacier will start thinning. So then eventually the larger percent of the glacier area will find itself in a warmer climate, so lower down, warmer climate, which will effectively cause the more negative mass balance and increase glacier runoff, increase meltwater production. So the glacier volume will start going down, it's thinning, and the meltwater production, the runoff from the glacier will start increasing with the climate warming signal. However, after some time, so we're still talking about climate warming, this low-lying part of the glacier will disappear, it will melt away. So effectively now, looking over the whole glacier, larger percent of glacier area will find itself in a cooler climate, more higher up. This will then cause decreased glacier thinning and less negative mass balance. It's still negative, just less negative. So it's effectively, it was less negative, so it's still negative, but it's less negative. And it will also cause decrease in glacier runoff. So effectively, because the glacier has shrank, it cannot produce as much meltwater as originally when it was a large glacier. So we are talking about this peak water, first initially increase and then decrease. Effectively, the response in mass balance and runoff, whether it's increasing or decreasing trend, will depend on whether the thinning process dominates or the shrinking process dominates. And also part of that process is dictated by the ice flow as well. That's why the ice flow models are important, because they are constantly redistributing mass down the glacier. So now to answer this first question, how much mass will glacier lose by the end of the century? So what I did some while ago is use exactly this modeling framework. And what I used in here for these components, for the global climate signal, I used historical and future global climate models, given climate scenarios. I used statistical downscaling, which I will briefly explain later. This is to translate the global climate to local climate, and then for the surface mass balance model, I use the simplest models, so models of low complexity, the temperature index models. For modeling accumulation, I just use precipitation when temperature was below given threshold, very often 0 degrees. And for the geometry changes, I used again simple model, just scaling relationship between the glacier volume and area. And with that, I applied this scheme to each single glacier in the world, and then summed up their volume change, and then calculated out the total volume change, what is the sea level equivalent. So that would be then the total glacier contribution to sea level rise. And here are the results. So I'm showing the projections of global glacier volume evolution in response to temperature and precipitation scenarios from an ensemble of 14 global climate models. And here I use two emission scenarios of greenhouse gases, the less extreme one on the left and more extreme one, and unfortunately the one that we are still on so this is more extreme emission scenario. So here I'm showing normalized volume of all the glaciers in the world, starting from 1. And this is the temperature and precipitation here averaged. So when all the grid cells from the model average over the over those areas that have glaciers, so over the glaciarized regions. So what here shows is that by the end of the century, I was focused only on the 21st century, the initial volume, the total volume change from its initial volume as a model mean of this 14 GCM is about 29%, which is the contribution of about 150 millimeters sea level equivalent, or sea level rise. And for more extreme scenario, it's 41% volume loss by the end of the century of its initial volume, and about 200 millimeters sea level rise as a model mean. But do observe that there is a large range of projections depending on which global climate model is used in these projections. So now this I've showed you just the global picture, and one can also differentiate that now in for the regions globally. So now I'm showing the regional volume change. Here I'm showing for the difference, this is for the 19 regions. Here in sea level equivalent, so how much contribution is from all the glaciers in the given region to the sea level, and this is the percentage of volume change in that given region. So again, in terms of biggest contributors to sea level, to global sea level rise, are those regions that have the biggest glaciers, those that have the most ice area. So they are Alaska, Arctic Canada, Russian Arctic, and also Antarctic and subantarctic. So not talking about the ice sheet, but all the glaciers that are surrounding the ice sheet of Antarctica. So they're looking more in terms of volume change, how much they percentage-wise each region lost glaciers by the end of the century. You can see that there are some regions that are not big contributors to sea level rise, but they are projected to lose more than 70% of their current ice volume by the end of the century. And these regions are Western Canada, so here almost like more than 80%. They're Iceland, Scandinavia, North Asia, Central Europe, Caucasus, low latitudes in the tropics of South America. So these are the regions that are not big contributors in terms of sea level rise, but for regional hydrology, it will make a huge impact because most of the glaciers might be gone by the end of this century.
Is Central Asia almost equivalent to Himalayas?
Yes. Although this region is also divided into multiple, so it's Central Asia, South Asia, and South Asia, East and West. So Himalayas are kind of divided there on 3 parts. So there is an observed huge scatter of projections for Himalayas, so there is large uncertainty. Now, just wanted to show you again the similar plot, but here instead of just showing the volume changes, I'm also showing the evolution of the runoff. So this is from the 18 regions. So as in blue is the volume evolution, again normalized, and in red is the runoff. So meltwater production from all the glaciers in given region. And in the gray is again for individual GCMs. So here what we can see is that we actually subdivided this 100 years of projection into sub-windows and calculated significance of trends in this kind of time series. So we found that most of the region have declined trend of runoff. So the meltwater is less and less being produced overall over the whole region, since this is the sum over all the glaciers. But some still have the rising trend, and some are projected, like Iceland, to have positive trend and then reaches this peak and then goes down, so negative trend. So just to remind you what this means, back to this peak, so whether thinning or shrinking dominates regarding the mass balance and the runoff. So overall, so what we're talking about here, that regions that have generally more positive trends, they are still, overall, so it's looking statistically, over all the glaciers in the region, the thinning more dominates than shrinking. And for those that are more on declining trend, the shrinking process, so the area retreat, dominates the thinning process. But this is again looking statistically over all the glaciers in the region. So my model was just one of the first models that started addressing these regional resolved projections of glacier contribution to sea level rise. And meanwhile, there were many other models, and they are all performed for the global scale assessment, and they are mainly using relatively simple models, those temperature index models, or like a volume area scaling approach in terms of glacier geometry change. So there are a bunch of models that one can classify as low complexity model. There is one model I worked on when I was a postdoc at UBC, led by my then mentor Gary Clark, and this is one of the only models that went further in terms of simulating for the regional scale only, not for global, this geometry changes using the two-dimensional ice flow models. So a little bit more advanced, but in terms of melt models, we are still with this temperature index model regime. So I was also part, and what I wanted to say about this is that the model, although it was higher complexity, did find that the largest uncertainty in the model comes from parameters that dictate surface melting, not so much about the ice flow. So effectively, we are in the climate that is so rapidly changing that what happens with the ice distribution, with the ice flow, doesn't matter. Glacier just melts, so it's almost so-called down wasting. So the ice dynamics do not matter that much because the melting is happening so fast that glacier is just thinning and shrinking really fast. So the ice flow distribution of that mass doesn't really matter that much, but it indeed matters how we model melt, because it will be highly sensitive to how one prescribes the model parameters in that model of glacier melt. So just wanted to show you also we did for the next IPCC that is now coming next year. We wanted to provide an intercomparison of all available current models for the glacier contribution to sea level rise on a global scale and also regionally resolved. So now this is projected relative mass changes by the end of the century for each region and also globally. Again, for 3 different scenarios, and each different dot here in color is different model. One of these is mine, I think this blue one. So it's this is the least extreme scenario, middle range, and the most extreme scenario. So what's interesting here is that on global scale, models agree relatively well, so not a large scatter in projections of how much glaciers will contribute to sea level rise, but regionally there are huge differences. So there are some large uncertainties just depending which glacier model is used. So this brings me to my next question. What are the key uncertainties in the projections and how to narrow then these uncertainties? So coming back to this modeling framework. So even though all these models do differ to some point, they generally use the same modeling scheme like that I just showed you, this flowchart. So effectively, the errors that will be in each of these components will propagate into and cause the final error in the results. So now I will step by step introduce what are these uncertainties in each of these components, and then I will talk about more in detail about each when I talk about how we can address and how we can make maybe progress in addressing these to narrow down the uncertainties. So starting from the top. There are biases in global climate models and in the scenarios, and so of course it's uncertain what actually the projections will be in terms of climate change. These transitioning from global climate to local climate is still performed with relatively simple downscaling methods, and they have limited application. We'll talk about this a little bit more. This surface mass balance, as I showed you already, it relies on these empirical models that are relatively low complexity, and they depend on observations. So whenever you have an empirical model, you need to tune it to observations, but there is lack of observations on glaciers. There is about only 1% of glaciers that have observed time series of these mass balance. So these models cannot be well constrained. Geometry changes, again, simplified models. Most of the models are using these scaling relationships. And also glacier calving, this iceberg calving process that I thought that it's also important for the tidewater glacier that's even not modeled in here. And then finally, there is the fact that we cannot really truly validate the model projections, because that's about future, but simulations of the past can also poorly be validated. So what happens here is that on individual scale, for some glacier we overestimate its volume loss, for some we underestimate, but then we rely that these biases will cancel each other. So if we are taking large enough sample of glaciers, let's say over a whole region with 1,000 glaciers, we are hoping that overestimations and underestimations of individual scale will cancel out. So we will get approximately good result. However, we cannot really confirm if this assumption is correct, because we are lacking observed historical changes on the regional scale. So these are the problems that now I will go into how we can address them. So starting from the top, we use the ensemble of GCMs, but we could use those global climate models that are the best performing climate models rather than all available climate models. So effectively, we could evaluate the models with the observed historical data, and then use the best performing models in the ensemble. This is how it's commonly done in terms of reducing the uncertainties in future climate scenarios. This part, using more advanced geometry changes models, it's only a matter of time when the global climate models when the global glacier models will start incorporating these ISO models. In fact, that already has happened. So the physics-based models, such as the one we used for Western Canada, that is just a matter of time when it will be applicable on the global scale. However, as found in this also research, is that what matters more is not that much how we simulate geometry changes, but the surface mass balance. And this is where I want to put more my research focus on. So the goal for that I've been going for last several years with the help of my grad students is to move from these empirical models to more physics-based models, which for glacier melt means to move to here to here. So in these empirical models, as I said, we need observations. So in the empirical models, the simplest one is to zoom to make this linear relationship between glacier melt and the sum of positive temperatures. So to find this seasonal melt over one summer, you sum up the daily temperatures when the temperatures are above zero. And there's a melt factor, like it's a constant, so the melt is proportional to sum of positive degree days, and this constant of proportionality is the melt factor, which is found glacier specific, meaning that it cannot universally, the same constant factor cannot be universally applied for those measured glaciers to unmeasured. So effectively, there is a huge uncertainty what is this melt factor. If we don't know, if we don't have observations, we cannot prescribe it. So huge uncertainty here. So instead of depending on these glacier-specific models, we could say, okay, leave these empirical models and move towards the physics-based models, because physics should be universally applicable to all the glaciers around the world. So by this I mean that the surface energy, that the energy available for melt at the glacier surface is simulated as the total sum of globals of the net short wave, net long wave, sensible latent heat fluxes. Here also the heat from rain and the heat into the snow and ice, which are small terms of this equation. So so I moved the research towards the surface energy balance model, but before we move into this modeling aspect of glacier contribution to sea level, I wanted to test how these surface energy balance models work if we measure all the fluxes. So not using them from the models, but measure them directly. So I invested into field seasons on the glaciers here in the Rockies of the Western Canada. On 3 glaciers, I was pretty much setting weather stations and measuring 4 components of radiation, turbulent fluxes, and so on, temperature, wind, and so on. And for this, I need to just credit it to my student who did, this is my grad student who recently graduated, who should take most of the credit for setting these weather stations and analyzing the data. So what we found, just here as briefly to the result, is if we measure at a given point surface lowering, so how much melt there is, and if we are measuring all the fluxes and closing this with and calculating how much surface lowering is in the model, we found that the two really match well. So if we measure all the terms in surface energy balance, we can model in the surface energy balance model, the modeled surface lowering and measured one come really close. So when we measure all these components of surface energy fluxes, the most tedious one are the turbulent fluxes, sensible latent heat fluxes. So exchange of heat through the turbulent eddies between air and the surface. So what we do when we measure these directly, we have sensors that measure 10 to 20 times in a second wind speed, temperature, humidity. So it's high frequency measurements, from which we then use so-called eddy covariance method to calculate, let's say, directly measure, or basically we calculate these surface fluxes. In reality, like more standardized measurements, of course, are not on this high frequency. Standard measurements, as you probably know, is like on 10 minutes, half an hour, hourly measurements, and also in the model, you have outputs of wind, temperature, precipitation, and so on that are on hourly scales. So effectively, we cannot use these, we cannot rely on these high frequency measurements if we want to calculate surface energy balance on glaciers. So what's commonly done is to use approximately methods that will rely on these mean measurements of, let's say, half an hourly values of wind, temperature, and so on. And so to approximate these sensible heat fluxes with so-called bulk aerodynamic methods, where so for the sensible heat flux, this bulk method will be proportional to, the sensible heat flux will be proportional to wind speed, measured at, let's say, 2 meters above the ground, and the difference between the temperature, the air temperature, and the surface temperature, and this difference. And for the sensible heat flux, it's the difference between the water vapor pressure at 2 meters and, let's say, at the surface level. So also here, as you can see, there is this exchange coefficient, the parameter that depends on the surface roughness length and on stability or stratification in that of the atmosphere that's near surface atmospheric level. So just to briefly introduce these concepts. So because the surface is rough, it will cause a drag or friction on the air that is flowing above it. So this friction, this surface roughness will effectively cause that the mean wind profile, or the profile of the mean wind, will look something like this. And then when we speak about the surface roughness length, that is the height above the surface at which wind, when we're going down this profile, reaches zero speed. In terms of stability, so what I want to say here is that the rougher the surface, these exchange coefficients will be higher. So that's the general concept here. In terms of stability, if we have cloudy conditions very well mixing in the atmosphere, so low local stability, generated so the generated turbulence with this process will be suppressed. So effectively what I want to say here is that the exchange coefficients will go down as stability increases. So this is the general theory, and it's being confirmed before on the crop fields, in the forests, and on many flat surfaces, where it's like where crop fields and forests and vegetation. However, the question is, do these bulk methods work well on glaciers? Okay. Since these measurements are really rare, they also require measurements of this high. If you want to compare how well the bulk methods work, we need to also measure directly the fluxes. And these directly measured fluxes with these high frequency instrumentations is maybe done on a handful of studies, not many. So what we wanted to test here is to see whether these bulk methods, the commonly used bulk methods, work on glacier. In fact, to see whether they satisfy two key assumptions. First key assumption in these bulk methods, in order for them to work, is that the fluxes of momentum and heat are constant with height in that surface boundary layer, so near the surface. And the other key assumption is, as the stability increases, this exchange coefficient should decrease, and we simulate that decrease through these empirically derived correction functions that are derived from, again, crop fields, forests, but not on glaciers. So, looking at the glacier, coming back to this first assumption, so during these cloudy conditions, we indeed get this profile of wind for which the first assumption should work well. However, much more common on glaciers is clear sky conditions, where we have high incoming short-wave radiation, where effectively, because the surface layer cannot increase above 0 degrees, the layer next to the surface will be colder because it's constantly losing its heat in contact with the surface. It will be cooler than the surrounding air. Effectively, it will be less buoyant, more dense, than the surrounding, and it will, because of the glacier slope, it will start sinking down. So this is this so-called katabatic wind, so sinking of the cold air down the glacier. When we have katabatic wind present, which is a prevailing condition on glaciers in clear sky conditions in summer, the wind profile looks more like this. So it's effectively decoupled from that free atmosphere wind profile. And when we have such a wind profile, this first assumption cannot hold. So this is the first problem. The second problem is this, as stability increases, the exchange coefficient should go down. So here the problem is, if we are looking at the local stability, indeed, if we have local stability such that it's higher, it should suppress turbulence, but looking at the stability over the valley scale or over the glacier scale, the larger stability means more enhanced katabatic wind. So stronger winds and more shearing close to the surface. Effectively, this mechanically generated turbulence should go up. So local stability, if it goes up, if it's connected to the also valley stability that is also then going up, effectively should increase production of turbulence because wind shearing is stronger, wind speeds are faster during katabatics, and so this, in a way, it's questionable whether it can hold at all. So what we were doing on these glaciers that I showed you where we had weather station, we compared the model momentum flux with those that are derived from these high frequency measurements. So let's call that observed momentum flux, and observed sensible heat flux with the modeled, and observed sensible and latent heat flux with the modeled. So what we found, just like here briefly, but here I'm showing the bulk method versus observations without any stability corrections and with stability corrections. But regardless of stability correction, what is shown is when we have katabatic winds prevailing, the performance is the worst. So we are severely overestimating the momentum flux during katabatics with these bulk methods, and we are also overestimating the sensible and latent heat fluxes. So effectively, what we concluded is that nothing of this holds, and now my new grad student is trying to introduce different ways of thinking about it. So we need better theories in order to address these problems. So the old methods cannot hold, so that means we need to develop new ones. So this is research in progress. Okay, how am I doing with time? Okay. So coming back to the next problem, and this is use of the simple statistical downscaling methods that have limited application, what I want to do here is we want to move towards dynamical downscaling combined with machine learning methods. So briefly about that. So if you have a field that you resolve on, let's say, 100-kilometer resolution, so as the global climate models output these grids that are nowadays up to, let's say, 80 kilometers, or maybe even 50 now, 50 kilometers resolution, you still cannot resolve these local processes that are relevant for glacial melt. So effectively, we talk about scale mismatch. So we have data, the climate fields on low resolution, and we require for understanding what's happening high resolution fields. So effectively, we want to speak about the process that will downscale those low resolution fields to the high resolution fields, or get from large scale into the local scale. So one way is to use statistical downscaling, which is done when you have observations on the local scale, and then you establish transfer function between the large scale variables and those observed ones. And then you assume that this established transfer function would hold in time and it will not change. So what is established over present climate will keep up and be also like that in the future with changing climate. That's already an assumption that is relatively weak, but also problem is that what if you don't have observations? In complex terrain on mountain glaciers, we don't have observations, often not. So the other way, maybe smarter way, is to use dynamical downscaling, which was effectively running a numerical model with all the physics equations of mass conservation, energy, momentum, like it's done in GCM, but on high resolution. So you nest, you put inside the global climate model the regional climate model that will produce output that uses the global climate model data as boundary conditions to all these equations, and then solves and outputs data on a much higher resolution. So this is called dynamical downscaling. So what nowadays the kind of state-of-the-art model is this weather research forecast model, or WRF. And there are very, very few papers testing this dynamical downscaling, how it works on glaciers, basically to downscale fields required for glacier modeling. So this is also an aspect that is now in progress. One of my students picked up, and the idea is to first try to see if we use this dynamical downscaling, force it first with past climate data, with the climate reanalysis in this case, that comes on 80 kilometer. If we downscale it to 2.5 or below kilometer scale to see how then we can simulate those fluxes that we have measured. So first would be the evaluation of this approach. Again, work in progress. And then I mentioned we want to use dynamical downscaling with machine learning methods. Okay, this has become my kind of passion in the last few years. It's machine learning. So in machine learning, that's a process of learning of a machine that tries to simulate the way how our neural networks in brain function. And in the geosciences, applications of machine learning are, those that I know of, are in forecast, hintcast, pattern recognition, and clustering. To very briefly explain it, so the process is such that we have an input data, let's say some kind of time series, spatiotemporal time series, and we have an output data as well, that is our target data. So what machine is doing, and you have these layers with neurons inside, is establishing connections between the input layer with the output layer that you also provide. So target data is provided. And then establishing the connections through the nonlinear functions that are connecting neuron to neuron in each different layer. And the whole thing works as an optimization. So you feed the input data and the output data as well, and then the model is learning how to, basically what's happening, it's optimizing its parameters in these nonlinear functions to replicate exactly the target data. So you are repeating this training process with lots of data. So here the trick is to have lots of data so that the machine can learn and effectively replicate the output data that you provide to the machine. So in this case, where I want us to go, I will not go in detail exactly how, but the idea would be, because these downscaling methods using this WRF, regional climate model, is very computationally expensive. So what I showed you that we want to do, we can do it maybe over 1 year and output hourly time series of temperature, wind speed, and so on. But if we want to do projections, we need 100 years of simulation. We need 100 years of this projected time series. And currently the computers that we use, like a supercomputing machine, is we need approximately half a day to produce the 1-day simulation. So one thing would be, okay, let's wait for 50 years to produce 25 years of simulation, or we need to find a faster way to achieve these high resolution fields. And this is when then machine learning that is much faster in terms of computational efficiency. And so the idea would be to feed in only maybe for several years, use the global climate model data for the present climate, and use these downscaled fields as a target data, and then let machine to establish the connections between the low resolution data and high resolution data. And then for the future projections, use now, once when the model is learned, use input as a global climate model future projections, and we will get projections of the highly resolved fields for the future period. So effectively, we are using trained machine to give us the projections on these high resolution fields. So this is the idea. And finally, the last aspect, it's this that we don't have observed historical changes in glacier mesh changes. Now that is being slowly covered with lots of remote sensing data, so more and more we have measurements of glacier shrinkage and glacier mass loss through the satellite data, but it's still providing, since it started in the 2000s, it's still relatively short time period of this data, and it's very often given its time as snapshots. So we need, what we actually need is a continuous time series of the mass changes. So here the idea is, instead of relying on these traditional mass balance observations, either they come from in situ measurements or from satellite data, we could use alternative data sets, such as streamflow data, river hydrographs, okay? And use that as a proxy, so learning something from the river streamflow about how the glaciers are changing. But this is tricky, use of proxies is tricky, so one question is, how can we identify signature of glaciers in the river? Okay. So this is then one of the main questions that my PhD student is asking Sam Anderson, who says, can the presence of glaciers be detected in available long-term streamflow data? So he studied the region for now is Alberta, where there are hundreds of glaciers, and he took, so here I'm showing the hydrographs from all the river gauges available in the region. So here from 139 stations upstream of dams, and from each of these stations he has daily flow rate from this period. So what Sam did, just briefly on that, is that he calculated the average seasonal hydrograph from each of the stations over all these years, and then ran this data through a clustering algorithm, here known also as the machine learning algorithm self-organizing maps. So here I'm showing what he found from this analysis is that there are approximately 6 clusters, as optimized number of clusters. So effectively each of these stations is associated with one of these clusters, and here I'm showing the mean pattern of mean hydrograph for each cluster. So each of the stations in the region is associated with one of these clusters. So this cluster here, cluster number 1, is the only one that has largest stream flow and slow decay over August season. So that's effectively when there is not much precipitation in summer in this region. The snow melt is gone, so the only contributing actually factor here that keeps in August stream flow high are the glaciers. So this method pulled out this unique cluster that is different from all the others, and indeed these unique clusters are identified close to the Rocky Mountains where the glaciers are, but also some down the stream. So what he found with this is that the glacier-fed rivers, so effectively those rivers that we now identify signatures of glaciers in the stream flow, have relatively high total summer August stream flow that makes them the unique, different from other streams. And they also, that I'm not showing here, have relatively low year-to-year variability, so from in that summer streamflow. So the idea here where this is heading to is that from changes in these glacier-fed rivers, how the streamflow is changing or how it changed through time, we can say something about then how glaciers have changed, how glacier runoff has changed in time. So this is like an inverse problem. From the output data, we can say something about the origins of the change. And this brings me to conclusion. So I talked about the importance of glaciers on the global scale in terms of sea level contributions. Current projections from here I'm showing for two emission scenarios are somewhere between 50 and 200 millimeters by the end of the century that it would be contribution of glaciers to global sea level rise. Then I talked about on regional scales how there are lots of problems in terms of each model has many uncertainties, and there are also uncertainties in this projection on regional scale in terms of which model we use. And I talked about the strategies that we are, that my team is trying to address in terms of narrowing down these uncertainties. So in terms of incorporating observations, empirical and physics-based modeling and machine learning methods. And finally, on a local scale, again, bring this aspect of why should we care? Effectively, none of these regional projections say anything about locally for the, let's say, for the local policymakers or for the end users, will your village, will your city, will your town notice that glaciers are gone? So on that level, and when will that happen? And will your drinking water be a problem, like your freshwater availability? Will it be at risk with the fact that there is climate change and the glaciers are gone in the region? So what we need, which is still missing, is the spatially resolved projections within that given region that are actually relevant for the local end users and policymakers. And this is our goal. We want to provide a risk assessment of glacier-fed freshwater resources under changing climate, starting from Western Canada, but effectively applying it to the whole globe. And with this, I'm ready for questions. Thank you.
Hvala lijepo. Evo, prostora za komentare, pitanja.
Možete na hrvatskom.
Da, pitanja malo. Čisto predavačice smo izašli u susret zbog tebe govor.
Jako zanimljivo, jako lijepo predavanje, drago mi je da sam bila u mogućnosti ga slušati. Ja imam, odnosno, dva pitanja. Jedno možda su ovako više naravi globalno što se tiče klimatskih promjena. Naime, u svim onim IPCC reportima smo slušali da kad je davno se krenuo tapati ledenjaci, da ono to proces koji je teško zaustaviti. Znači, kada smo hipotetički sada temperaturu obratili na neku, reći, umjerenu razinu, bismo li time zaustavili otapanje?
Čini se da su već glečeri izašli iz te neke ravnoteže. Znači da se sada i zaustavi, oni su već iznad tog ekvilibrijuma, izvan tog ekvilibrijuma. Znači, recimo, da bi se sad stvarno oni obnovili, znači nije samo pitanje otapanje, nego i akumulacija. Znači, trebali bi u toj novoj klimi, kakva je, imati ne samo već više kiše, nego više snijega.
Znači, morali bi temperaturu još spustiti?
Temperature, recimo, ostanu na ovom nivou, ali trebalo bi onda, znači, do više snijega, što još uvijek pokazuje da će biti vlažnija planeta sa vlažnija i toplija planeta, ali ovdje je bitno to da je snijega, ne kiša. Jer iako što te projekcije pokazuju da ukupna oborina raste, ta oborina je nama bitna za glečere je snijeg, ne kiša.
Znači pa bi trebalo na neki način pokušati izvrtiti kotača nazad?
Za neke glečere to je već prekasno i mnogi su već i pokopnili, više ih nema. Gotovo i manji glečeri u Alpama i čak i u zapadnom dijelu Kanade.
I drugo što me zanima, ono jednadžbe koja je u stvari, gdje se računaju tokovi, gdje ulazi albedo, naravno. Koliko je on vremenski ovisan ili se smatra konstantno?
Vremenski ovisan i najzanimljiviji dio je kada je prelazak iz snijega na led. Znači, kad smo jednom riješili snijega, onda taj led nema toliko veliku variabilnost, oko 0,3 albedo, 0,2 do 0,3. Međutim, snijeg, pogotovo ako još pada snijeg i po ljeti, na primjer, to strašno promijeni albedo, recimo sa 0,2 krene na 0,8, 0,9. ali recimo ovaj snijeg što ostaje duže dok se snijeg ne oformi u led, što traje godinama, još uvijek je taj albedo. Znači, jako je bitno postići kad točno prelazi iz snijega u led i kad su te oborine preko ljeta koje bi onda preko tih dana onda umanjile zapravo otapanje zbog toga što je albedo manji, veći.
Vezano uz modeliranje govornika, jel ste uopće isprobali korištenje regionalnog klimatskog modela u smislu znači postojećih baza koje se jeste to isprobali? Vidim da ste išli direktno sa globalnim, da li ste ikad u međukoraku nekakvom, vidim da ste na 2,5 km, razumijem, ali...
Da. Radili smo regionalne kad smo radili ovaj regional glaciation model za zapadnu Kanadu. Ali to je bilo sve znači nismo išli na regionalno za projekcije, nego za povijesne. Da. I onda opet sve za projekcije se opet baziraju, ti regionalni se opet baziraju znači, na emisijama koji su samo napravljeni za globalne. Znači vi ne radite ove emisije, ove RCP emission scenarios, se ne rade za regionalne. Dakle, opet ti regionalni uzimaju onda boundary conditions, te rubne uvjete ali nismo išli na ove koji su već bili dostupni na većoj na toj većoj rezoluciji, a mnogi od njih samo rade interpolaciju, što je isto, recimo neki raniji studiji su koristili samo osnovnu interpolaciju, kao što je Prism Data, na primjer, koji napravio interpolaciju, znači nije zapravo da vrti numeričke modele, nego interpolira globalne. Ali za sada nismo, zato je zato to sad želimo napraviti, da napravimo WRF, koji bi onda regionalno proizveo, znači za čitavu regiju i se na recimo kilometar rezolucije vrtile te projekcije. Ali onda ne možemo to napraviti za 100 godina jer je prespora simulacija.
Da, efekti su vjerojatno puno izraženiji.
Ali inače regionalno još niko nije koristio ništa veće od recimo, ne znam, bilo je neki 30 km rezolucija, što je još uvijek, ako je Glacier 2-3 km površina,
ima ovih cortex baza koje su na 12 pa sam čisto mislila da ste se možda s time igrali pa vidjeli kako vam je uspjeh u tome, jer nije uvijek, ne bi možda baš bio čovjek bi intuitivno očekivao da će odmah biti poboljšanje, makar ne mora nužno biti, tako da čisto me zanima vaše iskustvo.
Ja nisam osobno, znam za nekog koji su probali prije, dok još nismo imali dobru rezoluciju o tome gdje su točno glacieri, ali sad bi mogli to popraviti, jer u međuvremenu se taj inventorij popravio. Glaciologija u neku još šepa za ostatkom meteorologije u smislu kako je to sve napredovalo. Mi smo se još dugo mučili s time da nismo ni znali gdje su nam točno glacieri, koliko ima glaciera, koja je površina svakog glaciera. To se tek nedavno ta baza podataka napunila i tek sad kreću, znači mi smo u nekakvom zaostatku sa ostatkom meteorologije. Nema baš puno niti komunikacije između glaciologa i meteorologa.
A drugo me zanima, da li je ova era 5, da li to planirate koristiti?
Da, to je sad izašlo i baš za ovaj rad što radi Sam i on baš koristili smo era interim prije, ali sad baš era 5. Ja se čak mislim isprobati s tim era 5, ne uopće ići sa ovaj downscaling, nego mislim direktno isprobati pa da vidim što će biti. A taj način iz 2 km možda bi se već nešto i moglo, tako da to mi je sad baš plan.
Aha, da, to čisto ovako je u glavi. I sad zadnje pitanje, ono što se pokazalo, znači onu sličicu sa nekakvim, ajmo reći, vertikalnim profilom ledenjaka isplanirane. Koliko su otprilike te dimenzije ledenjaka na tim slopovima planina?
Znači, ovi manji glacieri su negdje 50 metara debljine, a ovi veći su po 300-400 metara debljine. Da.
Ne, čisto zato što kao onaj termin warm climate i cold climate na 50 metara mi je malo.
Da, ali govorimo o tome što su oni uz tu, znači, taj elevation range je dostavlja, to zna biti po 1000 metara, mislim. Da, ali znači nije da ih samo, da, to je oko 1000 metara, oni naravno manji koji su se već povukli, oni već imaju manji taj range. Ali mi govorimo o onome, recimo imate te glaciere koji imaju veliki jezik u dolini, a gore akumulacijska zona koja bude po 1000 do 2000 3000 metara iznad. I to je onda stvarno taj efekt lapse rate velik.
Aha, to me zanima. Nisam se, ja se slike nisam imala osjećaj dimenzije.
A sama debljina je isto, koji može doprinijeti isto tome, jer 500 metara na ovoj veći glacieri su debeli toliko.
Možete malo pojasniti kako se outputi globalnih klimatskih modela koriste za ove projekcije doprinosa od glaciera s obzirom na horizontalne skale outputa globalnih modela i samog glaciera? Kako, pretpostavljam ste ovdje uzeli svih 2100 glaciera planinskih?
200.000, da. 200.000 glaciera, svaki pojedinačni, da.
Pa ako možete malo samo objasniti na koji način ta metoda radi, jer ovo mi je dramatičan broj.
Ok, znači na koji način radimo, na koji način uzimamo od globalnih klimatskih modela output da bi onda vrtili ove lokalne?
Da.
Da, evo, ima li tu kakva kreda? Ima, odlično. Znači ovo sad, pokušam malo to sve jednostavno objasniti. Znači ako imamo output, recimo ovo sad na nekakvoj outputu globalnog klimatskog modela, kao mreža. Sad ja imam u jednoj njegovoj ćeliji, imam nekoliko glaciera. Ok, sad su oni sve tu recimo, ako su u recimo 100 km i mogu mi tu nekoliko glaciera stati. Znači ono što ja znam, ovdje mi trebaju lokalni podaci, temperature, oborine i tako sve što mi ulazi recimo za melt. Mi treba melt factor i lokalna temperatura. A ja imam samo ovu dobivnu na 100 km. Znači ono što ja radim, ja koristim ovu koja je od te ćelije na 100 metara, ali treba mi onda mjerenje, treba imati mjerenje ovoga koliko je otapanje, to što kad pričamo o jednostavnim modelima, i onda ovaj faktor ovdje, ili uspostavljam zapravo lapse rate, ja znam koja mi je visina te ćelije, znači grid cell, na kojoj je visini taj model da, i znam koja je visina glaciera, i najjednostavnije onda uspostaviti da je lapse rate, znači da mi je promjena temperature zbog toga što je ćelija dobivena na jednoj visini, a glacier mi na drugoj.
Jer ovisi o vertikalnoj rezoluciji.
O vertikalno, to je pojednostavljeno, nisu to samo, znači to nije sad stvarno vertikalna razlika, nego to je neka statistička. A to je najjednostavnija prva, recimo, pretpostavka. I onda kad imam tu temperaturu koja je sada znači smanjena ili povišena s obzirom na lapse rate, onda mi je ovaj faktor bitan i onda moram ga zapravo kalibrirati ili tuning da bi uspostavila najveće odgovaranje između mjerenog otapanja i ovo koje je modelirano. Znači ovo je zapravo kalibriran faktor, onda ispada da za svaki glacier koji je u ovoj tu ćeliji, taj faktor je zapravo nešto drugačiji. Zato je problem onda kad nemam ovo mjerenje, koji ću ja faktor prepisati ovim ostalim glacierima.
Dobro, i povezano za to, onda za svaku od ovih krivulja, za svakog globalnih modela, mi sad govorimo o nepouzdanosti, gledajući raspon između 14 globalnih modela. Međutim, tu postoji i intervalne sigurnosti za svaki od modela.
Da.
Ali to nije prikazano.
Ne, nije to prikazano jer je ne prikazano znači kolike su nesigurnosti u samim temperaturama i projekcijama svakog pojedinačnog modela, i to zapravo niti ne znam da govorimo o projekcijama. Znači mogu se postaviti ti intervali s obzirom kako taj model simulira prošlu klimu. Recimo svaki klimatski model ima historijske simulacije i buduće. Za budućnost ne znamo kolika će biti nesigurnost, ali za prošle znamo da možemo prepisati taj sličan raspon nesigurnosti u budućnosti, na primjer. A ono što ispada da je zapravo ono što oni rade je ne vrte model samo jednom, nego malo promijene početne uvjete i onda ponovno izvrte model za prošlost i za budućnost. I onda se i tako zapravo procjenjuje kroz te sensitivity tests, što se mijenjaju ti početni uvjeti, se procijeni kolika je zapravo taj raspon nesigurnosti. Ispada da je taj raspon nesigurnosti u istom to nekom rangu kao taj raspon nesigurnosti zbog tih modela, zbog toga što koristimo različite modele, znači ovaj GCM raspon je identičan jednom rasponu od jednog modela, ali zbog tih početnih uvjeta. Da, to je zapravo jedini način na koji možemo baš ocijeniti nepouzdanosti u pojedinim modelima.
Hvala, ništa. Ja mislim, evo nema više pitanja, ali u svakom slučaju mislim da trebamo još jedanput zahvaliti predavačici. I evo, ovi stidljivi imaju prilike pitati predavačici sad ovako. Mislim da